I don't think I need to introduce Amin to this audience. So Amin Vahdat is a fellow at Google and also our area technical lead for networking, which means that he's responsible for the overall technical direction for networking. And he works with lots of people in this room as far as technical leadership around networking. So we're really excited to have him and Bikash start us off today. Thank you.
Okay, so welcome everybody. It's a real pleasure to be here. First, I want to make sure that we take a moment to thank Negar. She organized this entire event for us, so a round of applause for her. This is about 3x or maybe 4x the typical event that Google organizes. I take blame or credit, depending on how you want to look at it for this. I really wanted to push for getting as many people here as possible. As those of you who are Google know, I've been looking forward to this day for a long, long time. My greatest pleasure walking around the halls at Google is looking at the density of great people that we have here at Google. I think we've built a great team here in industry, but I'm also really thrilled because looking around here, it's tough to think that there's been much better density of amazing academic folks anywhere gathered. So this has been something that I've been excited about. I took it upon myself to try to put together a new talk for you all, so you'll have to bear with me. This is maybe very different from any talk that I've given before in that I'm not going to be describing a system that we've built or a novel, awesome, wonderful thing that we've innovated on. I'm going to try to talk about how we think about problems and some of the challenges that I wish we could solve. My overall goal, as Anis was also mentioning, is to get people talking. I think that we've already gotten off to a great start over the past hour plus. So, please continue to exchange ideas. Again, I think that you'd be hard-pressed to find a better gathering of the best minds in networking. So I hope that some great connections get made among the academics in the room, and of course, back and forth with the folks at Google. Okay, so with that, let me give you my perspective on networking research at Google. I think where we really benefit is that we're driven by novel application requirements and really massive scale. So we do research like everybody else does. We're presented with problems that we don't know how to solve. And these problems come from our application developers running very exciting new services. On the other hand, of course, it works both ways. We think about what we can do on the networking to make the lives of our application developers easier, to allow them to do things that they couldn't otherwise do. The impact of what we can do can be huge. We, again, serve some substantial fraction of all internet traffic. Right? And that means that if we can do something new, novel, it can have a huge impact. That's the positive. The maybe positive, maybe less positive, I think it's overall a huge positive, is there is no tech transfer. I think that all the teams that Denise alluded to, we are the product team. Right? If we come up with a good idea, we only have to convince ourselves to do it. But that also means that if it breaks, we're the ones who have to fix it. So we are the product team. There is nobody to transfer things over to. But what this means is that we can sometimes anticipate shifts in networking research. And what I've been pushing for over the past few years is to also make sure that we can give back and publish more and more of what we do. So just to put this in a little bit of perspective, Google has a long history of really foundational work in distributed computing, starting with, say, GFS, over to MapReduce, Bigtable, et cetera, leading to TensorFlow and Spanner more recently. Many of you sort of dually work in the systems and the networking community, so many of these efforts are probably familiar to you from various SOSP, OSDI, and other papers. But again, the thing that hasn't been as clear is that this distributed computing infrastructure from GFS to TensorFlow required a networking infrastructure that you couldn't buy. And that's where we have the privilege of working on the systems that we do. So more or less matching some of the innovations on the distributed computing infrastructure side have been a number of things that we've gone after on the networking side, starting perhaps with the Google Global Cache, our content distribution network, to some of our data center networking work, Watchtower, Freedom, more recently Jupyter, our wide area network like B4, Most recently, we've done a lot of work in protocols, QUIC, BBR, gRPC, etc. And over the past 3 or 4 years, we've been increasingly active. This is in publishing. So rather than just doing the work internally, we've also been doing more and more publication of our efforts. This is a subset of some of the papers that we've published over the past 3 or 4 years. On the distributed computing infrastructure side, open source historically has been about us publishing papers and others picking up the efforts and doing some very important open source efforts around it. I don't have on this slide TensorFlow, but I think TensorFlow is a good example of how we're shifting things, where we're going open source from the very beginning with some of our distributed computing infrastructure. And I think you're seeing the exact same thing happening on the networking side, with efforts like QUIC, TCP BBR, gRPC, and OpenConfig. These are just 4 recent examples of efforts where we're using these actively at scale within Google, and we're open sourcing the exact same code for use by the community. And the ... here indicates that we're looking to continue this model, push on this model moving forward as well. Okay, so with that, in terms of a little bit of background of how we think about networking research at Google, let me shift over to what I see as some of the next decade challenges in networking. So we've been publishing a lot in software-defined networking, in protocols, congestion control protocols, etc. But I actually do think that now is an interesting time to be thinking about what's next, because I personally actually see the light at the end of the tunnel in terms of some of the efforts that have been going on over the past 5 or 10 years or so. That's not to say that we're done. We have a lot of work to do internally. There's a lot of great research to be done externally, but I also see that it is an interesting time to be thinking about how things are going to be shifting in terms of important topics over the next decade. So one of I see maybe 3 general areas, and they wind up being pretty closely related. I'll talk about at least 2 of them in some more detail. One is serverless compute in Cloud 3.0. What I mean by serverless compute is that I think we're going to be moving away from specifying individual virtual machines that are configured in particular ways, running fairly coarse-grained services, to individual functions that get run and scale out as they need. I'll talk about that more in a second. IoT is a buzz phrase right now, the Internet of Things. What I do think this means is that we're going to see a substantial shift in security requirements, but also the number of streams and the number of flows that we have to manage across the internet and back to data centers, as well as, of course, the security and privacy concerns that go along with it. And finally, I think that we've been seeing this over the past 5 years, but it's really starting to hit home and hurt now. The ability to get more performance, and even by more performance, I mean more parallelism, more cores from individual servers, is slowing to maybe stopping. And what this means is that for us to be able to get more performance out of our computing infrastructure, more efficiency, and maybe most importantly for us to be able to go after bigger problems, and that's really what it comes down to. It's not about performance and efficiency so much as being able to do problems of a scale that we couldn't do before. We're going to have to go after more tightly coupled general purpose distributed computing infrastructure. And what I mean by this is that we have to be able to bring 10, 40, 100, 1,000 servers to bear, communicating interactively, synchronously at very fine time scales, right, moving toward microseconds on problems. And this is a big shift in how we build applications. But we can't build applications like this because the network doesn't yet support it. I'll be talking about this one a bit more as well. So overall, I see an opportunity for us to put together a lot of the themes that the networking community has been working on for a while. One of these is what I'm here calling agile scale. I'll describe what that means in a moment, but it's not just about scalability in the traditional sense. Jitter has, of course, been a long-standing issue in networking. I'll talk about how it hits us at multiple points in the end-to-end system to really hurt what we can do. Isolation among computing that is sharing the same infrastructure. And what all this says is that if we can get agile scale, if we can manage jitter, if we can deliver isolation, we can potentially deliver transformative performance, but it's only meaningful if we have the basics, and the basics are availability, manageability, and velocity. I'm not going to talk about manageability much because my colleague Bikash Koley is going to have an entire great talk on that topic, but that's not to say that it's not super important. It is. Okay, so let me set the stage a bit with some of the things I'm seeing on the compute side and some of the things that we're going after already at Google. So last decade, maybe 10 years ago, starting about 10 years ago, we were in the era of Cloud 1.0. Here, we saw that virtualization could deliver savings in capital expenditures to enterprise data centers. So that's a mouthful. What does that mean? That means that I could take my existing hardware that I had and run more workload on it because I could have 5, 10 virtual machines configured exactly the way that I needed them to be configured, running on one piece of hardware. So I could take my data center and really run it much more efficiently. And this was a huge win. I think where we are right now is Cloud 2.0. And what we're seeing is a move to hardware on demand. I can get those exact same benefits, but I no longer have to run my own data center to do it. I can now expand or shrink my computing infrastructure on demand without having to figure out how to build out my computing infrastructure, the hardware underneath. At the same time, I'm still having to configure all my computing infrastructure. I have to figure out exactly how my virtual machines are supposed to run in terms of operating system, in terms of network policy, and everything else. I've moved from buying hardware middle boxes to buying software middle boxes. I still have to configure my firewall rules just like I did before. In fact, I prefer to configure my firewall rules exactly like I did before. I want to be able to take exactly what I did in my enterprise and run it in the cloud. But I can now shrink down, expand out on demand. And this is also a big win. However, I think where we're going is Cloud 3.0, where we can shift away from servers, away from virtual machines, away from individual rules, firewall rules for individual servers, load balancing among individual virtual machines, et cetera, toward compute. So serverless compute says, I can focus on what I do best, which is my business logic, let's say, whatever it is that my application needs to be doing, not on exactly where my data is placed, not on how I load balance among virtual machines, not on how I configure the operating system on individual machines, how I patch them to make sure that they're secure, et cetera. And so from a researching perspective, we should be aiming for Cloud 3.0. And one of the things that I think hurts is when we think more in terms of how do I take the things that I've always done in my enterprise data center and move it wholesale into the cloud. While that's familiar and maybe easy to think about in terms of optimization, it actually might be setting us back. Because in the end, this isn't how computing should be working, right? No one wants to be thinking in terms of my 1,000 virtual machines becoming 2,000 virtual machines and how I configure them. That I think in terms of being able to really focus on the next generation is maybe backward routes. So what are some of the specific items? I think storage disaggregation is going to be really interesting if we're going to be focusing on compute, where the data center is the storage appliance. I'm not thinking about where my data happens to be living. Transparent live migration we found is very important. And what this means is that I can move compute around anywhere within the data center and maybe even between data centers without having to expose that out to the customer. So while this isn't necessarily an end customer benefit from the perspective of delivering availability, manageability, et cetera, being able to move things around with no impact, essentially. What that means is that the customers, and by the way, the customers are often paying very close attention, don't notice as you're moving them around. Seamless telemetry, I want to be able to have exposure to everything that's happening in my infrastructure, not necessarily to expose to end customers, but to be able to scale up and down my compute. If I'm going to get to a serverless model and not be thinking about individual virtual machines, I need to be able to scale up and down my computation in response to load, but also while maintaining some higher level metrics, service level objectives in terms of latency, in terms of throughput. And then finally, this one is deceptively simple perhaps, but I think has some really interesting implications for networking, and that's an open marketplace. Think of this as an app store for virtual computing. I want to be able to buy services. Maybe it's a filer, maybe it's a security appliance, and be able to plug it into my network without knowing exactly how I'm plugging it into my network in terms of IP address configuration, et cetera. Right, so how do I expose third-party services into my computing infrastructure in a secure way while allowing them to have the privileges they need to add value for me? Okay, so what this means is we need to focus on applications, maybe even functions, not virtual machines. We want to specify what the policy is. Here's my service level objective in terms of latency, not what the middle boxes are, where they run, how packets are routed through them, et cetera. Right, again, so also SLOs, not placements, not load balancing, not scheduling. That's what the network, the system underneath you should be delivering. And finally, from a network perspective, I want to have actionable intelligence. And what this means is that I want to be able to have queries that are running live over my data without me having to go ask questions all the time. So not thinking explicitly about data processing. So what are some of the research and development challenges that go along with realizing some of this? I'll put them in order: availability, manageability, velocity, isolation, and performance. But I think it's important to also say how we think about things in terms of going after research challenges, development challenges at Google. So many of us absolutely love performance. Right? And that's the thing that we love to work on more than anything else. It's the thing that we can measure. It's the thing that we can brag about. We're 2.4x faster than the last thing. All that actually is the last thing that we work on, at least when we're going after things at Google. And what I want to stress is that there are tremendous research challenges that lay the foundation for going after performance. I won't lie, I love performance as much or more than all of you. But it's the thing that you go after last once you have the basics in place. And it's the basics that allow you to go after the performance. So number one is availability. And we're seeing just tremendous requirements. We've always had them in terms of delivering the highest levels of availability. 5 nines, 99.999%. One, what does that really mean? We struggle with that internally. Right? It's easy to say no more than 5 minutes of downtime a year. But what does downtime mean? There's failure in our network all the time. 100% of the time, there's failure. Right? But just defining what that means for us, it's something that Bikash and I talk about multiple times a week. Right? What does availability actually mean? And what does it mean for us to be delivering 99.999% availability? Okay, so that's the basics. And for us, it's gotten even more important because internal Google services can be written to tolerate failures a bit better than cloud-hosted services. So as we've made the shift to cloud, it's become even more critical for us because we can't tell all the engineers out there, oh, here's how you manage an entire data center going away. Right? For internal customers, search, they know how to manage an entire data center going away without anybody externally noticing. Much harder to do for external customers. Okay, so manageability. We've made it available. How do we make sure that it's manageable? We have one of the world's largest infrastructures. It's changing and growing all the time. We can't have hundreds of thousands of people, millions of people, if we stay on certain tracks, trying to manage the infrastructure. It just doesn't work for many, many reasons. So that's requirement number 2. Velocity is an interesting one, and I think it starts really getting at the heart of systems. How do we make sure that we can upgrade our infrastructure very, very quickly? How do we make sure that we can roll out a change across the fleet in a week, every week? And maintain availability. So those two things are in sort of huge tension. And figuring out system structures for managing that is probably some of the biggest intellectual contributions that we've collectively made at Google internally over the years. And this is in service, by the way, of performance in the end. You're going to be constantly optimizing. Your workload's going to be constantly shifting. You're going to be coming up with better ideas. You want your ideas to have impact. You want to roll it out across the fleet. how do you do so safely every week? So velocity is just absolutely key. Stranding. This will come into tension with another requirement that I'm going to mention, which is isolation. But we want to make sure that for our infrastructure, that we, again, have some of the largest in the world, we're not losing a bunch sitting around idle. Okay, because frankly, that's the biggest performance optimization we can get, is if we have idle cycles that aren't doing anything, well, we can do a lot better in going from 0 to 1 than we can go from 1 to 1.1 or 1.2. So that's the bottom of the pyramid, and then comes performance. So what I want to encourage maybe all of you, and certainly, and by when I say all of you, I mean Google and academia, what ideas can we go after to enable the basics: availability, manageability, velocity, stranding, so we can all go after performance even more. Okay, so hopefully I've made this point. Availability is just absolutely paramount. For me, this includes security, and insecure infrastructure is an unavailable infrastructure. I'll say maybe the obvious: Google's infrastructure is under attack. Just like something is unavailable all the time, it's under attack all the time, just 24/7. The magnitude of the attack changes, and there have been some that have worried us as well, but security I'll take as primary. Stability is more important than efficiency, and that gets to my point about velocity. So if you can, I'll trade an inefficient system for a stable system. Already mentioned the point about network management. Bikash will be talking about that more. Configuration is hard. So here, it's surprisingly hard to impossible for me to ask the question, what does Google's network look like right now? I don't think anybody knows. Right? We have pretty good ideas of the truth, but we don't really know. More surprising, what did we mean for the network to look like right now? We might be able to get the answer to that, but not as easily as we might like. So managing config is super hard, and I think there's room for improvement. So I talked about manageability. One of the ways to make sure that our infrastructure is manageable is to aggressively automate, but this can be counter to availability. So one of the things that we're seeing is that automation can run amok, and pulling human judgment out of the loop can be dangerous. We covered some of these topics in a recent SICOM paper, so I'll refer you to that if you're interested. And there's a really great book that was recently published out of Google on site reliability engineering that I also encourage you to look at if you're interested. So build for velocity. I was inspired by, I guess it's 10, 12 years old now, paper, Tesla in Cyberspace, Defining Tomorrow's Internet at SICOM. What I took away from this paper was that the internet was undergoing ossification because we couldn't change it. And this is really my point about velocity. How do you build systems so you can change it? And the internet was, of course, was stuck in this place where the only way you could change it was to get multilateral agreement among thousands of participants. I think we've broken out of that tussle, but I think it has a great lesson for how we build systems for velocity from day one, build it for upgradability. What we say oftentimes here at Google is launch and iterate. What's the minimum viable product you can get out there that's better than the last thing, and iterate from there. Okay, I talked about stranding, but I think that the other very related point is, and these are interesting counters to one another, we think that isolation is critical, but stranding is terrible. So this goes back to the old debate about work conserving versus non-work conserving. We multiplex many, many different applications on the same physical infrastructure. And all of these applications want the illusion of running on their own hardware. Our biggest application developers really want the illusion of running on their own hardware, and sometimes they even get it. But in general, we can't afford it. And yet we think stranding is terrible. So how do we balance this tension? So purpose-built infrastructure works, but we can't do it very often. The thing I also want to point out about isolation is that this is really what congestion control is about. It's also applies to the control plane tremendously. So some of the interesting things that we see is, especially in the cloud world, if you want to, or in a serverless compute world, what if you want to spin up thousands of instances of a function? You want to make sure that you spinning up your 1,000 instances of a function doesn't impact someone else spinning up 1,000,000 instances of their function. Right? So it's control plane, it's data plane, it's everything in between. Okay, so I'm running short on time. We will have some time for questions. Let me try to make one last point before handing things over to Bikash so that we stay on target. And maybe this is a somewhat new thing that we're seeing here, is probably from a typical grizzled Google engineer's perspective, nothing bothers them about reading a research paper more than scale benchmarks that go to 5 or 10 or 100 endpoints. So scale is interesting, right? If you can scale linearly to 5, 10, or 100, that's very good. But what we're seeing here is that real distributed applications communicate with thousands of endpoints, and real servers host hundreds of applications today. And if we're going to go to a serverless world, they're going to host 100x that in the next few years. Most of them won't be active. Right? But what this means is that we can have tens of thousands of endpoints per server, maybe hundreds of thousands of endpoints per server, all of whom need to potentially be able to go from 0 to 100 gigabits per second in 0 time. Right? So this is what I mean by agile scale. How do I manage with low latency and efficiency the ability to manage tens of thousands, let's say hundreds of thousands of endpoints, and have any small subset of them use all the resources of the server essentially on 0 notice? So it's relatively easy to get great performance when I have 100 endpoints all talking to 100 endpoints for many, many minutes or hours. Much harder if that subset of 10 or 100 is changing at very fine timescales. Okay, and I think if anyone is interested, I will tell them a little bit about some of the distributed computing programming models that we're seeing and what Google would like to shift to moving forward. But for now, I'm going to stop with the conclusions and hand things over to Bikash. I think that now is a great time to be thinking about the next shift in networking research. And I think this is really driven by more tightly coupled compute and a serverless compute model, moving away from individual servers and individual VMs. And I think that to really go after these things, we have a great opportunity to put together a lot of the threads and ideas that we've been pursuing over, well, multiple decades. Okay, so I'll stop. And did you want to take questions now, Anis, or at the end? Okay, so with that, I'll hand it over to Bikash then.
Thanks very much, Amin. So just before bringing up Bikash, I neglected to thank Nigar for her heroic efforts. So thank you, Amin, for doing that. All of you who've worked with Nigar, communications, food, transportation, the program, the website, everything. She's kind of superwoman for this program. So thanks very much. And also just wanted to call out Jeff as well. So all of you know Jeff really well. I was just assistant to Jeff, but Jeff really was working hard to put together the entire program, the format, a lot of that stuff. So really want to recognize Jeff. Please thank him when you run into him. So next we want to have, the next keynote is by Bikash Koley, who runs, as I mentioned, our network architecture, engineering, and planning and design teams, all part of network operations at Google. And he's also a distinguished engineer at Google. So please welcome Bikash.
Thank you, Anis, Jeff, Nigar, for putting this together. You know, I haven't seen this kind of crowd in a relatively small room, all packed here. You know, talk about the performance density in this room. You know, we tried to get better weather for you, but we thought that for this conference, I think cloud is appropriate. So we did what we could. But we'll mostly be indoors today, so it'll be great. You know, I wanted to start with, you know, pointing out something that we learned at Google. You know, building networks for, you know, it's my 10th year here for the last 10 years. there is a traditional tension between operators and developers in the outside world, where operators do not like change, developers love feature, and stuff don't get delivered because operators push back and developers want to launch their thing, and it's a bad cycle, right? The first thing that we learned to fix at Google is that you cannot scale, evolve, or develop features if you actually maintain this developer-operator boundary. And so one of the things that you're noticing is that it's a research conference, but it's hosted by me coming from the operations side of the house and Amin coming from the developer side of the house. Two of us actually spend more time every week than I probably spend with my team, or he spends with his team. It's actually key to this talk. I'm actually going to point out why this is important, because first is organization. If you don't fix organization, you actually don't fix the product that you build. And then we tried very hard to not have this traditional separation between operator and developer. We both research, we both develop. Our necks are equally on the line when things break. We both care about performance and stability and scaling at the same time, right? So what I actually wanted to do is to share some of the lessons that we learned, some of the things that we have actually tried to do with our infrastructure, and then really leave with seeing if that triggers some thoughts that you have on research ideas, and then we obviously can continue the conversation as we move forward, right? So roughly, we're going to talk about what it really takes to operate a very large network. I will share some actual stats on how large this network is. Amin talked about high availability in the network, and literally, like, this is one of the biggest things that we think about all the time. I'll share some of the insights as to why high availability is hard in an infrastructure like this. The forgotten plan, the management plan. One of the things that we often talk about, and we actually read papers a lot, all of us do. And we see awesome, wonderful papers in control plane and data plane and service virtualization. We would love to see great papers in management plane. There is a lot to be done there, and we're actually going to talk about why it's important that we actually fix that plane. And then having thought about this for quite some time here, we'll share how we're trying to solve this massive problem that we have. And of course, we are not done solving this at all. So really, it is here to trigger your interest in this, what I call the forgotten plan, and how we go about solving it, right? So as Amin said, for the last 15 years, we've been building the largest cloud infrastructure in the world. We've been building cloud before cloud was a thing, or it was named cloud. We have always built this, right? And the global network that we have built is sort of the fundamental building block of how cloud works, because the main thing about cloud is ubiquity. You basically want the services to be available everywhere in the world, and what makes that possible is network. The network itself doesn't look any different from any of the other cloud provider, I would guess, right? We actually have very large data center networks that connects all of our servers. We have an inter-data center network that connects these data centers together, and we have a global backbone that allows the services that run on these data centers to connect to the internet and to the users, right? How big? It's actually very big. This is actually showing both our inter-data center backbone, also known as B4, and internet-facing backbone, also known as B2. They're overlaid together, along with all the various submarine and terrestrial capacity that we have. Our internet-facing backbone, or B2, connects 70+ locations in 33 countries. It's basically global. You have heard a lot about the inter-data center backbone, B4, which is fully SDN, fully homegrown, and really built from the grounds up to really do one thing well, to connect the services between our data centers and really to help them transfer large amount of data as well as replications. How big? Well, that picture is nice. You have seen those pictures many times with other talks. So let me actually share some actual stats. Our network today has 30,000+ circuits. Most of those are actually 100 gig, so you can do the mental math of how big the network is. It's very big, and it's growing at a very rapid pace. our network has many tens of network element roles. Actually, it's more like hundreds of network element roles, and they're individual functions, and therefore it comes with their individual configurations and things that happen with that. Our dozen plus vendor, including ourselves, we actually count ourselves as one of the suppliers of the technology. It's a massively large supplier of technology in this network. 4 million lines of configuration files and growing every single day. 30,000 configuration changes per month, and these are massive configuration changes. 8 million object identifiers that we collect every 5 minutes. All of that is growing at an exponential scale every year. So when you look at this large scale, there is one thing that is constant, and Amin mentioned that, that is outage. Happens all the time. Every single day, at every single minute, there is something in the network that breaks. Now, not all those outages actually lead to service outage on the network. We design our network very carefully where we're designed for failure, where things break, but really we still try and offer the same SLO that our services actually expect out of network. That, by the way, is hard. And it's hard because, again, Amin mentioned how we try to build our infrastructure where often the requirement is 5.9 or better. If you break 5.9 down into the way that we actually like viewing availability, what availability really means is by a term called outage budget. That's really what matters. It's not the average availability number that you use, right? So 5.9 gives you 24 seconds of outage budget in a month. So compare that with what I just stated, that every minute something is breaking in the infrastructure. And you have 24 seconds of total outage budget for your services, or your network can be unavailable to your service, right? Which basically would mean that the network would not meet the SLA that we actually advertise to our services, like packet loss, latency, et cetera, right? It's very, very, very tight budget. And when somebody loosely said 5.9, so you should keep in the back of your mind 24 seconds. It's less than a minute of total outage that you're actually committing to. So we actually spend a lot of time in figuring out what's the best way that we can offer the availability that our applications need. And especially with cloud, the need for high availability is actually growing for the reasons that actually Amin mentioned in the previous talk. And what we did is, we have this tool that we use internally called Postmortem. The goal of this tool is to have completely blameless analysis of why something went bad in our infrastructure, and then find root cause, and then go after fixing the root cause so it doesn't happen in the future, right? So we have this very rich data set of 10 years worth of postmortem on things that have broken in the network. And what we did is we went about classifying what leads to these outages. Some of this is actually covered in the paper that Amin mentioned, the Evolve and Die paper in SIGCOMM. But we actually had a very interesting observation out of this classification. Irrespective of the underlying technology that we have in the network. And as I mentioned, like we have a data center network, which is fully SDN, you heard of Jupyter, the inter-data center network, which is fully SDN P4, and we have an internet-facing backbone that's a more traditional IP MPLS backbone with some amount of SDN on it. So very different technologies. But when we went through the classification of outages in these different pieces of the network, we found that they all have a common cause of most prominent outage. 70% of the outages, approximately, in all this infrastructure lead from management operation to the network. Now, let me spend a little bit more time on that. That's actually a very important finding that we had, which is not to say that we don't have fiber cut, we don't have router failures, we don't have optics that goes bad. That all happens. But all of that constitutes only 30% of the cases where the network actually had an outage. The interesting observation with the management plane outage is that most of the time where we see outages that happen out of a management plane operation, they're mostly related to changes that were not intended by the management plane change that was actually applied. So let me give you an example, right? I wanted to reboot a router and somebody applied a wildcard while rebooting the router. Like that'll be a classic example of how it is the unintended change that breaks the network down. In many cases, it can also be I applied a change to one part of the network and I did not realize the impact of that change to another part of the network. A classic example is BGP policy on a router. I might have applied a BGP policy for one reason into one router, and I did not realize how the nature of the traffic is going to change in the network when I do that. And the main reason for this is these networks are too big to keep the state in the head of a network or a software engineer, no matter how smart they are. And I'm very proud that we actually have some of the smartest in the world that does this, and they make mistakes, which basically means that any infrastructure that you run, the operator will make mistake because that is too much state to keep in a human's head, right? And that's where most of these failures actually start from. So as someone who has to operate this very large infrastructure, the question that we always ask ourselves, what are we trying to solve? Like, what is my elevator pitch as to what we're trying to solve? Of course, the first one is we want to build the best, cheapest, the highest performing, the most reliable, the most scalable network in the world for Google. Like that is a given. But really, what is the problem statement that we're trying to solve? The problem statement that we're trying to solve is that I have these three things that I'm trying to constantly optimize for: reliability, scale, and efficiency. And what we always find is that it is very easy to optimize for 2 out of 3. It is extremely difficult to optimize for all 3. So let me give you an example. So I mentioned that 70% of the outages happen in our network when we make a change to the network, right? When our network is most stable, where nothing breaks, it's between Christmas and New Year's Eve, because we don't make any changes in the network. There are hardly any outages that happen, right? So one way of making our network reliable and actually efficient as well, and I'll tell you how it's going to be efficient, but one way of making our network very reliable is to never make a change. We'll basically have 5 days of network refresh time every year, and that's the only time you get to make a change in the network, and the network is going to be super, super reliable. It's also going to be efficient. You know how it's going to be efficient? It's going to be efficient because, well, you are just going to keep on oversubscribing the network because you're not making any change, right? So, your unit cost of using the network, well, it's going to be very nice. It will not scale, right? It will absolutely not scale because you're not touching the network, right? Flip side, how can I make it scale and make it reliable, but maybe efficiency is harder? Well, you can solve that by money. I can make it very reliable by building everything twice, and it'll actually scale just fine because we'll actually throw the money at the problem, right? It'll not be efficient, right? So that sort of gives you an idea of how it's very easy to solve 2 of them, but it's actually very hard to solve all 3, right? Our goal, as I think of my charter, Amin's charter, ASP's charter, and others that lead networking in here, is to turn this triangle into a straight line. This is what we're trying to solve. What we're trying to solve is we want to have a mechanism of running and operating the network where reliability, efficiency, and scaling, they're actually coupled, and you get all 3 when you make a change in the network. How can we get there? How can we get there where we actually are solving not the 2 of them, but the 3 of them all at the same time? So it comes from the realization that the way to solve the reliability problem in the network is to make the management operation safe. Now let's start from that point. If your management operation is safe, then that basically means by extension that I can touch the network as often as I want, which means that I can evolve the network as often as I want, which means that I can introduce new technologies to the network as often as I want, which is how you get efficiency in the network, because you're basically replacing an old technology with a new that is just better, more efficient, cheaper, bigger in size, right? So the more often that you can do that, the more efficient your network is. That also means that you can scale the network faster, right? Because if you go to the example of the data center technology that Amin mentioned, going from Saturn to Jupiter, it is few orders of magnitude higher scaling. So if we can do this every week and every month, that actually means that you are scaling it much faster, where your scaling is not brute force or spending money, right? So that sort of gives you sort of the core tenet of what you're trying to solve. And this is why I mentioned why management plan is so important, but we don't talk about it often, right? If you solve the problem of making management reliable, you actually are very close to solving this linear evolution problem, right? And then the one thing that is constant in this is evolution is constant in Google's network, because if we don't evolve, we actually don't launch new services, we don't support new customers, and we actually don't reach the new users that we need to use, right? So ultimately, evolution has to happen, right? So we basically came to the conclusion that we have to solve the safe management plan problem to get to there. And that fundamentally led to an architecture that we called the zero-touch network. So what is this architecture about, right? It all comes from the insight that there is too much state that operators need to maintain in their head when they do traditional network operations. And that is the primary reason for network breaking. So the way that we solve that is by reducing the amount of state that any network operator has to carry. And the state is managed by what is best at managing it, software, not human. So effectively, it starts from these following points, that first, all network operations are completely automated, where a network operator requires no steps beyond instantiating the intent. And intent in this case is very high level. I want to create this MPLS tunnel from A to B is way too detailed, right? My intent would be, I need connectivity from A to B with this SLA, right? It's a very high level intent that we want an individual to apply. A human is never required to apply changes to network elements. The changes that are ultimately applied to network elements are actually computed by a system based on this very high-level intent that the network operator creates. So ultimately, a human never interacts with the network elements themselves, right? The software system does. Third one, super important, right? When you look at, we talked about the outage budget, right? That Five9 has an outage budget of 25 seconds. There are several ways that you can reduce outage budget. But one thing that we learned, again, over many years, the most important thing that you do is you reduce your MTTR, mean time to repair, which means that you reduce your mean time to detection, and then you go and fix the problem as quickly as you can before it melts down, right? So the approach that we have here is that we actually want to halt any network change that even has indications of things going bad, and then you get the network back to a state where it's safe. And this happens automatically. You don't wait for a human to apply judgment as to what the state needs to be. The system does that for you. So you basically have reduced the outage time that you have consumed, the outage budget that you have consumed. Last one, equally important, right? The system itself should stop a human from making any changes to the network that are not applied, that are not allowed by policy. What does that mean? These are actually very high-level policies. These are things like, you are not allowed to take down more than X% of capacity in metro in a location, right? Or you are not allowed to reboot more than this many devices in the network, right? And realize that this policy is almost impossible for a human to fully enforce. However, a human always use intuition, where they know that if I'm probably touching more than 5 routers, I should not be touching, right? So this is bringing the human intuition into the system, but ensuring the system itself is applying the policy where the policy is described by the network operators, right? So what do the operators really do in this system? The operators write the policies that describes how the network will remain safe. The operator describes the intents, and these intents come from what they do on a daily basis with the network, not with the elements. It's a big difference in how we look at this, right? It's not interacting with the elements themselves; it's interacting with the structure that we have, and the system provides a safeguard, right? Where things will go wrong, but the system provides the safeguard. So I'll very briefly touch upon the architecture. We can discuss this more into our breaks. I'll not spend a whole lot of time on it, but really let's walk through the basic idea, right? So the basic idea is that what an operator really interacts with is a workflow engine. An operator never interacts with the elements that are underneath. The workflow engines are essentially finite state machines where the operator writes a graph. And the graph basically says what I want the network to do if I have this intent, right? The workflow engine interacts with the network systems through a set of very well-defined CRUD APIs, right? And we call them intent APIs. And these CRUD APIs are very high level. They're actually not element specific. They describe the change to the network structure, right? How do they describe the change to the network structure? They do that through a set of network models that we have built. And we have 2 types of models that we actually maintain in the network. There's a topology model. I'll talk a little bit about that. It's actually an interesting research topic. And configuration model, right? And these intent APIs are actually making changes to these network models. Again, they're not making changes to the elements themselves, right? Changes to these models are then used to produce the changes in configuration that you ultimately want to produce for these devices. All happens in software. It does not happen by human intervention. And the last but the most important part is that unlike traditional routers where the changes are traditionally imperative, where you actually interact with the devices over CLI in many cases, and you do transactional changes to the devices, all these changes are fully declarative. Why is it important? It is important because of the question that Amin asked. Do we know what state the network is in? We want to know what configuration these devices have. We don't want to derive it. We want to know exactly what the configuration these devices have. So it's fully declarative. We know exactly what configuration has been pushed in the device before it has been pushed. And by the way, this is not generated by human. They're in the config DB. So if things break, we know exactly how to roll back to a safe state because we know the previous configuration when the network was operating well, right? And it was safe. Briefly on network models, there are two sets of models that we actually have built here, and I've spent many years building them because this is a very interesting research problem really for us to solve. The first one we call, actually, let's start with the configuration model. This, by the way, is open source. We call it OpenConfig. It basically describes any of the policy or protocols that we have to configure in our network in a structured way. And it's an object model. It uses Yang as the language because it has been standardized in ITF. And the list of the models that we have is evolving. And we actually welcome many of you to sort of take a look at the repository that we have in GitHub and actually contribute if you want to. The second one is something that we developed internally at Google. What we realized is that we had many descriptions of what are fundamentally graphs. That describe network structure. We had some for optical, we had some for MPLS, we had some for BGP mesh, we had some for our fabric and cluster. It was a mess. And so we ended up developing an internal model, which we call UNM, or Unified Network Model. And the idea being that any structure that can be described as a graph and it's definitely applied for network, but it could be things like line cuts in a chassis, for example. They're described in this unified model. They're in protocol buffer and etc. Right. Last part, I'll just spend my last 2 minutes in this because it's super important, and then I'll stop here. Which is, I mentioned that the only way that you actually can reduce your error budget is by knowing when the network is melting down and then stopping the meltdown of the network. I talked about stopping the meltdown of the network, which is you have declarative configuration, the good state, you get the network back to the good state when meltdown is happening. How do you know when a meltdown is happening? So what you realize is that the traditional telemetries that are used in network, specifically SNMP, they're just not good enough for doing it. The reason being that anytime you want to have high resolution data of which needs to be exported in high volume out of the router, you start trading off router performance with telemetry, which is a really bad trade-off to have, right? So instead, what we ended up going with is something that we've been using with our servers, with our cooling systems, with our CPU fans for a decade at Google. We stream telemetry data. We don't pre-process them in the element before sending them out. We stream them, and there is a streaming collector, and then we're basically able to export as much data as we want from the system because we actually have the collection system that are built. We relied on yet another open source technology that Google has open source called gRPC, and gRPC has some of the gRPC creators are here. Jayant is here. We have this beautiful things where we have bidirectional streaming, and it's secure, and we take advantage of that, and we use the OpenConfig models because basically if you're exporting operational state, it's no different than the object model that you use to configure those states, right? So you use a combination of those to actually use streaming telemetry to export the data. Combination of these has been super powerful in basically enabling us to make very rapid changes to our network, right? And the thought that I want to leave you with is echoing Amin's point, is performance is super critical. But the way that you get to performance is by launching things very rapidly and launching often, because you don't get to 2x the performance in a day. You get to 2x the performance by making changes every week, right? And the system that we build, we focus very hard on how we can allow changes to our infrastructure every week or every day, but don't trade off reliability in doing so, right? So ZTN is one answer to that, and of course, this is not the only answer, and would love to hear more from your more about your thoughts as to how you feel this problem can be solved. Thank you very much for your time.